not so fun? So, a couple of announcements before we get started today. Number one, Assignment 1 has been released. You can find it both on Avenue and on JupyterHub. So JupyterHub is now up and running. If you'd like to get all of that online and log in and find all of the stuff that you need to find, you are now clear to do so. Furthermore, Assignment 1 is due Sunday midnight. So you have a week to figure it out minimally. You should be fully prepared to do everything that's on Assignment 1 by the end of this class, maybe the first hour of next class, depending on how it goes. Furthermore, if you have any trouble with the setup and installation of the Jupyter system, we now have a very lovely tutorial document which you may peruse at your leisure, which you may find highly informative for the entire logging in process, local download and installation, anything you need, really. So if you're having difficulty with the whole Jupyter thing, please check out this document first and let us know if you find it helpful or not. If you don't find it helpful, it's possible we could improve the document, but we require your feedback to do so. So please take a look at the resources available. If you're still stumped, then please feel free to get in contact with one of the TAs. In particular, the tutorials that you'll be having today are the place where I expect the TAs to get you guys online with all of the systems involved. And I guess that's another way of saying we have tutorials today. So any questions about any of that? Okay, good. Might as well move right along with the lecture today then. So, last time we talked about quite a lot of stuff, mostly how one goes about writing expressions in computing languages. Various types, this discussion kind of had a subtext, a theme that ran through it of data types, right? We were talking about integers, we were talking about floating point numbers, and I'm going to try it with the projection, just the voice projection, just see how that goes. Let's see, give me a second. Unlock the door. What door am I unlocking? Let's see here. There we go. All right. I know it's not an especially large room, but I noticed that the voice is a little bit quiet in the videos, so you have to crank the volume. And while I think it's still audible at like full volume, what if you crank the volume and then the next thing, you don't remember that you cranked the volume, and it's like, for the next thing you listen to.
Hello, testing. Can you hear me in the back? Wonderful. All right. Is this like too loud? Are you guys okay with this? Is this a good level of volume? Excellent. Might save my throat too. It's a 3-hour class after all. Anywho, so we went through a whole bunch of different types of data. You'll notice that the type of a piece of data is a very, very important concept in computing. Different types are represented in different ways in the underlying memory structures that compose the machine. We had gone through floating point numbers, brief introduction. They get a lot more complicated. Integers, fairly simple. Booleans, simpler still. And then we talked about our first aggregate data structure, which is the tuple. Some of the people who've used programming languages before in the class were exploring the differences between tuples in Python and various other data structures that you're likely to have encountered in other languages, such as the array. Just to briefly recap, tuples are immutable data structures. Immutable, i.e. cannot be changed or mutated after creation. there are certain there are certain operations that you would expect for a data structure that are illegal operations over tuples. For example, you cannot select any particular element out of a tuple and modify it after the creation of the tuple with an assignment statement. This is a valid operation on lists, for example. Lists are a type of aggregate data structure that we're going to discuss in some detail this week. But this is not a legal operation over tuples. So, yeah. Another very important thing to remember about tuples, which throws off a lot of people who are just beginning their programming journey, this and many other data structures are zero indexed. That is indexed. That is to say, the indexing starts at the number 0 and then continues up to n minus 1, where n is the number of elements in the data structure. There are very good reasons for this that get into the way that these data structures are addressed. Essentially, if you want to dig into the nuts and bolts of how these things are actually represented, taking, for example, the language C, from which most of these types of languages are derived, a data structure in C, this guy right here, is actually a memory location indicating the first memory cell in which that data is being stored. So, to say T element 0 is also to say T with no memory address offset, which is why T at 0 is just the first element of that memory structure. So this makes complete sense if you think of this in terms of memory cell offset from the beginning of the memory structure, but that's not something that you'll be tested on in this course. That's just in case you were interested in why it would start counting at 0 instead of counting like counting 1. One thing to keep in mind, though, more or less every computer language that you will ever use will use this indexing scheme. So it's good to get used to it. It takes a little getting used to, but you do eventually get used to it. Any questions about tuples before we move on to strings? Good. So, we are now going to talk about strings. Strings are a very important type of data that is used by programming languages. So, a string is a sequence of characters, very similar to a tuple in many respects, especially in Python. In Python, strings, like tuples, are also immutable. Once created, they cannot be modified except through destruction and recreation, which is possible, but you know, we'll go through how to do that. So, in Python, when you create a string, it is delimited, that is to say, it is contained with either double or single quote marks. This is in contrast to a lot of other programming languages that you may have used, where single quotes and double quotes mean different things. And I know this is a Python class, but it's also intro programming, so I feel it's useful to, you know, for you guys to not fall into those types of pitfalls, because in most languages, single quotes indicate a single character, whereas in Python, it means a full string. Python does this interesting thing of pretending that characters don't exist. Any character in Python is actually a string containing only one element. That's how it's dealt with underneath the under the hood. So, so single quotes and double quotes are used interchangeably. This is also true of like a handful of other languages like SQL, but in most C-based languages, this would have to be a single character. So what do I mean by character? This is, a whole bunch of, maybe I should define my terms, huh? So what a string really and actually is, in memory, right? Let's say you have a segment of memory, right? A series of memory cells. Hello world would be the character H, the character E, the character L, lowercase l, which looks like one, I know. L, O, space, or actually comma and then space, and then the rest of it, right? And then I'll just put a little bit more on the end. Last character, that's just an ellipsis. Last character is the exclamation mark, and then, very important, all strings are terminated with a null character. But we don't really have to, get into that. That's going to be more, if you go on study C, we don't really have to worry about the null character in Python, but you should know it's there. So, a string, very similarly to a tuple, is a linear collection of individual elements. These elements happen to be characters. Now, in contrast to tuples, a tuple can contain anything as its elements, right? You can put numbers in there, you can put other strings in there, you can put other tuples in there, you can put booleans in there. It's agnostic as to the type of the elements inside of it. In strings, all of the elements inside of the string have to be characters. It's a tight constraint. So each one of these, it's important to understand, each one of these is designated by an individual series of ones and zeros, in the same way that numbers are designated by a series of ones and zeros. This is a computer. Everything inside of it is encoded in binary. The question, though, is, how precisely is this thing encoded? Well, it turns out that there's a standard for it. The first 128 letters, which corresponds to 7 bits, is standardized for any computer that is following the standard. And, at this point, it's pretty much all computers have been standardized in this way. Back in the, back in the 70s and 80s, there would have been different standards in different, countries and language groups. But at this point, we've extended the character set sufficiently that all of the characters from all of the languages have representation if you go beyond 127. So we no longer need, specific character sets for specific countries. We have what's called the Universal Text Format, UTF, right? So, at any rate, it's still important to understand how ASCII works, though, because this is the first 127 characters that exist. So, if we consider capital H, right? Capital H is right... Oh, it's going the wrong way. Right there. So, the number 72 is what is actually stored in memory when we say character capital H. So, what's actually stored in memory would be 72, whatever lowercase e is, 101, 101, ... etc., etc. You get the idea. Take this, convert it to binary, and that's what the actual memory underneath of it looks like, right? So the idea is, although everything is stored in binary, because the computer knows to interpret... Hello?
This thing is just running out of batteries? Hello?
Okay. Sorry about that, folks. So because the computer knows to interpret these memory cells as characters, then it will use them appropriately. If it doesn't know that this is character data, it's just binary ones and zeros. It could be integers, it could be floating points. We don't know, right? So the one thing about characters, which is interesting in comparison to something else like floating point or integers, we actually have a fairly limited number of characters relative to the number of numbers that it's useful to represent. I believe UTF, that is to say, the universal encoding of all characters that's currently good. Where was I? Characters, right. So it's important also to know that not all characters show up as visible letters. Many of the characters that we use are what we call control characters. These indicate what are essentially instructions inside of the string itself, which can tell you how the string is to be displayed, right? Most particularly, we have characters for tab and new line. So I think it's probably easiest to just do this in terminal. So if I have a string, hello world, and I print that string, it just prints out, right? The way that you access control characters, you actually need two characters to be able to write a control character. Because, you know, many of them haven't been mapped usefully onto your keyboard, so you require two key presses, right? So with control characters, you first type the backslash character, and then whatever character after that indicates the control character that you want to write. So, for example, if I do Control T, and then I print it, you have to actually print it, I think. That will actually show the, get out of here. Yeah, there you go. So you see how it gave me an extra gap there? That's actually a tab character. If you put 2 in, then you get a big tab, right? So the backslash T will insert however many characters are required to align it by default to 8 inside of this terminal environment. Tabs are kind of like one of the most controversial things in computing for a programmer, because nobody can agree on how many spaces a tab should be. Some people think a tab should be 4 spaces, some think it should be 8 spaces, some even think it should be 2 spaces, in which case, why not just use 2 spaces, you know? But anyway, so tab character is one. Another one is the new line character, which is, well, it does exactly what it says on the box. It inserts a new line. It inserts a line break. So anytime you have a file that has more than one line in it, the way that it's stored in the computer's memory is as one continuous sequence of numbers that represent characters interspersed with this new line character. And when the computer renders that file to you, it displays it, it inserts the line breaks anywhere it encounters a new line character. Does all of this make sense so far? This isn't too bad, right? Good. So that's characters. These are sometimes called the ordinal numbers of these characters. In fact, you can look up what the underlying ASCII representation is of any number in Python by using ord, which stands for ordinal. So there you go. Cool? So that's what a character is. Strings are just linear arrangements of characters. So now we know what both strings and characters are. I will reiterate, in Python, the Python environment itself does not differentiate between characters and strings. A string and a character are the same thing as far as Python is concerned. A character is just a string that contains one character, right? This, if you're programming in any other language, like C++, if you confuse these two, then you will cause yourself no end of headache. Another thing that's true about strings, which kind of, it's something that gets back to the very early days of computing, but it's a very useful thing. Strings in their representation, like they always have one character at the end called the null character, which denotes the end of the string. This is in there for basically the C programming language doesn't check the bounds on data structures. So the solution that they came up with at the time was to include an extra character at the end of a string, which denotes the end of the string, so that you can look for that, right? The null character in the ASCII table is actually denoted by a 0. So, and it's generally written \0. Don't use this in the string, or else the computer will think that the string ends before it actually does. Basically, just leave that one alone. And again, that's not really that useful for Python, but you know, we'll move on. So in Python, these are known as string literals. So in the same way that if we write the number 3, we call that an integer literal, or we write true, that's a Boolean literal. In the case of strings, if you just write a word and close it in quotes, that is a string literal. Note that without these quotation marks, Python will consider this as like Python code, not like something that you just wrote that you'd like to assign it, right? It doesn't know that you intend this as a character, a set of characters, unless you enclose it with the quotation marks. So if you were to enter hello world into the terminal without the enclosing quotation marks, it would be like, I'm unable to interpret hello, I don't know what command you mean, right? So, yeah. Does that make sense? Good. Any questions so far? Good. So, in addition to new line, tab, and null, there are 2 other uses of the / escape character that I'd like to review with you. Number 1, it may be observed, if you're using double quotes to indicate the beginning and the end of the string, how do you actually include those in the string itself, right? Because if you were to, for example, say s is equal to Nick the prof Moore, right? We have a problem because rather than include these double quotes as characters in the string, it denotes the end of the string because that's what double quotes do. I think I have to replace the battery on this thing. It's just getting annoying. Used batteries. New batteries. There we go. All right. Hello. Test, 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 test. Good. Hopefully that cuts in and out less. So, in most programming languages, you only have one solution to this. If you include an escape character before the quotation mark, that escapes the quote and gives you an actual quote mark character. So, all you need to do, include the backslashes and there you go. It includes them the way that you would expect. In Python, you have an alternative way of doing this. If you use single quotes on the outside, then double quote, single quotes on the outside. There we go. Then use of double quotes within is permitted in an unrestricted manner. And the opposite is the case as well. If you use double quotes on the outside, single quotes are permitted on the inside as many times as you like. So I know that that's a lot of technical detail, which might be like a little bit boring to listen to. But this kind of I would like to impress upon all of you that this type of knowledge is what separates someone who knows how to program from someone who doesn't, right? It's all of these tiny little technical details that that allow you to write programs, right? Has anybody tried doing any Python programming since last week? A couple of people? It's not as easy as it looks, right? Like, syntax errors are totally a thing, right? Unless you produce a program which is perfect to the character, that program will not be accepted as a valid program, right? So you, you should manage your expectations, right? Because, absolutely nobody can produce a program perfectly the first time, right? That's why you write it, you check to see if it compiles, you get the compiler to tell you where the problems are, then you try it, you fix them and try again. It's an iterative process. Nobody writes a program, nobody's like, okay, I want to write a program to, write a checkers engine or something and just sits down, bangs the whole thing out, no errors. That's not a feasible human activity, But eventually, for your program to work, you have to know all of these tiny little rules of grammar, and you have to be able to write them all perfectly eventually, otherwise the program won't eventually work. And since the thing you're being graded on in this class is, do you actually eventually get the program to work, you will eventually need to know this. So that's why we go through all of these tiny little seemingly insignificant details of grammar, because, essentially, not knowing something like this is something that can take you hours to figure out on your own if you don't know this is the problem, right? And I want you guys to avoid all of the common pitfalls as far as that's possible. That's kind of the purpose of the class. So, anyway, so we already talked about characters. Ooh, okay. One brief historical note, because I love brief historical notes. The ASCII characters were actually originally developed for electric typewriters So you get some interesting characters in the original ASCII set that don't really make any sense in the context of a modern computer, like Carriage Return. So if you know how a typewriter is set up, you have like this reel that you put the paper in, and then you have a print head that types the individual letters out on it, right? So this thing on the top that you put the paper in is called the carriage, right? So the way that a typewriter works is as you type, it moves the carriage like over this way, right? And then at the end of a line, it ding, and it usually has a little bell. Carriage Return is a character in the operation code set of the ASCII, but it really doesn't make a whole lot of sense in the context of modern computing, although various organizations have tried to find some alternative use for it. The other thing is bell is right here, character 7. So like when Carriage Return happens and then the bell rings, the bell was an actual character code on the typewriter itself. Obviously, when we were designing what the modern computer interface should be, basically what happened is they took like the nearest thing to hand which did the thing they wanted, which was an electric typewriter, and tried to wire that up into a computer, and that's how you end up with keyboards, right? And that's also why we end up with the ASCII layout or not ASCII, the QWERTY layout for keyboards. Basically, QWERTY is good enough that nobody. It's not worth the effort of changing the keyboard format to something that would be like more natural. Like anybody heard of a Dvorak keyboard? Okay, so Dvorak is like it's an alternative keyboard layout that puts the more commonly used letters in the middle, which are closest to like your middle finger and your index finger, which are the most nimble of your fingers, right? So in theory, someone who was proficient at touch typing on a Dvorak keyboard would be able to type faster than on a QWERTY keyboard just because it works better mechanically with your fingers. But it's such a fractional advantage over QWERTY that and it takes it would take like years to train yourself to be as good on a Dvorak as a QWERTY. Well, maybe not years, but months anyway. It's not worth the effort, so everybody just stays with QWERTY, even though it's not the optimal format. But anyway, so there's a little bit of keyboard history for you. So I've already kind of talked about this. But the first 128 characters, which were originally mapped to American and British typewriters, of course, only represented characters from the English alphabet. As computers became, a thing that pretty much everybody decided was going to be useful, no matter where you lived in the world, it became necessary to represent more characters from different languages, right? And accented characters, and all of the characters that we would want, right? So the original ASCII representation used 7 bits. They extended that to a full byte, which doubled the number of characters you could support. This was still not enough, so we now have Unicode, which is the international standard for character encoding. Emoji are Unicode characters. There are actually a very large number of Unicode characters that do not denote letters. It's actually kind of cool. If you take a look at Wikipedia, Unicode. Let's see. Where is my list of Unicode characters? List of Unicode characters. All right, here we go. So, if you take a look, we've got this column here gives you the character itself. So you've got the first bit, which is ASCII, right? the first, like, insofar as an ASCII code, an ASCII letter is defined in Unicode, it has the same number as in ASCII, just for compatibility, right? But yeah, you can see we quickly get into accented characters, upper and lower case. We get into Greek characters. We get into every character that you could possibly want. Cyrillic characters. And then you start getting into interesting ones like math symbols, currency symbols, extended math symbols. And one of my favorites, table characters. You know, you can actually like draw a chessboard using these like corners and edges and intersections and all that, which I sometimes enjoy doing when I'm writing, you know, test questions and that sort of thing. But yeah, so Unicode, very, very cool, very important. So yeah, you know how they keep adding more emojis over time? Basically what they're doing is the Unicode standard is expanding, and they're defining new characters, new character codes. And you'll notice, maybe sometimes you notice that like some emoji render in Apple but not in Android, right? Like you get a little box. It's like they all have to use the same Unicode encoding. It's basically a font problem, right? Some fonts will render some of the some characters, other fonts won't, right? So if you think about like the full Unicode, the full set of Unicode, and this was some while ago, quite a while ago. I think it's up to at least 142,000 now that we're dealing with. You can imagine that like creating a font that represents 142,000 characters. That's no small endeavor, right? So not every font will represent every character, right? So, you know, Android has some that Apple doesn't, and Apple has some that Android doesn't. You know, it is what it is. But anyway, so that's how emoji work. That's why you can send pictures, because you're not actually sending pictures. You're sending encoded numbers, which your phone decodes and you know, prints out as a smiley face or whatever. Good. So, in Python, Python files are UTF-8 encoded by default. You can include Unicode characters by their number inside of any string by doing /u and then a numeric representation of that number in hexadecimal. We're going to be talking about hexadecimal a bit later on. But yeah, in general, it'll work as well if you just like copy the Unicode character into the string. So there you go. So you can use Unicode characters. In fact, there's a question in an upcoming assignment that requires you to. So, operations on strings. Strings are linear data structures. So, similarly to tuples, we have indexing operations which are defined over them. So if you want to pick out a particular character out of a string, s at 6, for instance, the 7th character is t. Remember, 0 indexing. So, it works exactly the same way as it does on lists and tuples. So let's talk about slicing. This is a thing that's kind of particular to Python, although other languages will support similar operations. it's possible to not only pick out a single character from a string, or a tuple or a list for that matter, you can select a subrange. So you can create a new string by selecting a subsection of an existing string. The way that you do this, you insert a colon character inside of your indexing phrase. The first number is the number you start at. The second number is 1 minus the number you end at. So, for example, if I wished to select index 3 to index 8, you can see I get this element, which under 0 indexing is index number 3, 3, 4, 5, 6, 7, excluding 8. Make sense? A couple of interesting caveats on that. If you leave out the first character, it assumes you meant from the beginning of the string. And if you leave out the second character, or the second number, it assumes you mean to the end of the string. If you leave out both, then it thinks you mean from the beginning to the end of the string, which is not much of a selection at all, because it's highly inclusive of everything that already exists in it. Does that make sense? Cool. This string slicing is one of those interesting little skills that, like, you can do actually rather a lot with it, more than you might think. In particular, once you start introducing the third parameter, which is not being shown on this slide, which is the number that you can count by, right? So if you add a third parameter, you can get every second element of the string starting with the first, right? Now this is actually wherever you start in the string, basically count by 2, right? So this is cool because, you know, in the past I've asked a question on a test where it's like, deal out the characters in the string like you're dealing cards, right? 1 to each person. You can actually, like, you can do that with a loop, sure, but you can do that very quickly with a string slice operation. You know, say you have, you know, 4 people. There you go. If you read that vertically, you'll see that you get the string reconstructed, which is kind of cool, right? So that's slicing. We also have our length operator, which simply gives us the number of characters in the string. Very, very handy thing to do, to know how to do. Often when you're writing loops that execute over a data structure, such as a string or a tuple, the terminating condition of that loop will be, you know, do this until I run out of items. How do you know when you run out of items? You check the length of the thing you're iterating over, right? We can also count occurrences of a substring within the string. So, for example, if I have the string S and I wanted to see how many times the lowercase o occurs, count O, it occurs 3 times. And if you want to find the index of the first occurrence, pardon me, of a character or a substring. Substring, incidentally, is just a smaller string that's contained within the larger string. Then you have the index operation. Index of. Find the index of this thing. Does that all make sense? You guys will have plenty of time to apply all of this during assignment 1. You'll get lots of practice in. And if you don't get practice in, if you don't feel you've had enough practice with this on assignment 1, then I highly encourage you to try some of the Python, the coding that Python problem sets, because those are also really useful. You'll be talking about those in tutorial. If not today, then the next day. Okay? Good. No questions at all? Is this just like so basic that everybody's going to get 100% on the test? Yeah? Good. All right. Cool. So, oh, incidentally, because today is a day with a tutorial, I'm just gonna we're gonna skip the breaks so that we can end 20 minutes early, right? So that you guys can have an opportunity to go get some lunch. Good. So, so strings are immutable in the same way that you can't modify a tuple after its point of creation. You can't modify a string after the point of its creation and still have it stored in the same memory cell, basically. What you can do is you can create a new string that contains a change and overwrite the old string with it, but that's different from overwriting an individual memory cell. Let's explore the difference. So, let's say, let's just have a string ABC. There we go. So we have the lowercase alphabet. You cannot do something like this. So if I try to access an individual element of the string and use an assignment operation to overwrite it, I am prevented from doing so by the grammar of the language. That constitutes a syntax error. Type error, string object does not support item assignment. So what do? Well, you do this. A is equal to A from the beginning to the element we wish to replace, concatenate that with the element we wish to put in there, and then we concatenate that with the same thing from the next element to the end. And you can see it inserts the U. Inserts the U. This is not the same thing, right? So what you expect to happen, right? Let's just say A, B, C, D, E, right? If you wanted to overwrite D with, say, capital E, or a capital, some other letter, what you expect to happen is you expect to just wipe that out and replace it with D, right? That is not possible with a string in Python because that operation is disallowed. What you can do instead is you can perform a slice operation to extract this portion, right? So that actually allocates new memory, right? It creates a new memory cell with the first elements. We then create a memory, we assign new memory that captures the end of it, right? we create a memory cell that contains the literal U, or I guess in this case we were doing uppercase D, right? Right? So these are just free floating in memory, right? Technically speaking, what A itself is, or like the name we've given to the string, that is a memory cell that indicates the beginning of the actual data structure. This is known as a pointer in C. In Python, we call this an alias. So A aliases the first element of the original structure, right? So we've extracted all of the bits that we want. Next, we use concatenation operations to construct a new one that contains the new change because we have stated, this concatenate that, right? Then, through use of the assignment operation, we overwrite this arrow, have it point to the new one. Because this is no longer used, it's basically junk data at this point. Programs have an operation called garbage collection, where pieces of data which are no longer used are deleted after a certain amount of time, of not be like having no reference to them. Like every once in a while, the program checks itself for, do I actually have references to all of the data which I've assigned for myself? And if it finds data that it doesn't actually have a reference to, it'll release those resources back to the operating system. So this would be deleted via garbage collection at some point after this assignment statement. But that's how this operation is actually working. It's a reasonably complex operation. And all this because Python thinks that strings should be immutable, and in most languages they are in fact mutable. But yeah, it provides you certain assurances, this type of thing. At any rate. Any questions about any of that? Yes? Sorry? Oh, this one, this single line.
Doesn't that just add it in between the string instead of changing?
Yes, that's the point I'm making. You can't do it this way with a string because strings are immutable. So you have to, you can still do it, but what you have to do is you have to create an updated string that contains the change and then tell the computer that's the new value of this data structure. Does that make sense? Any other questions? Yeah. So I know this is like a complicated example, but this is how computers think, right? These are the types of operations that you do. If the computer's not doing what you want it to, you can usually force it to somehow. And this is these types of workarounds are unfortunately very common. Anyway, so here are some more operations on strings. Similarly to tuples, and as demonstrated in the previous example, if we use the addition operator, we get concatenation. That's what this operation is called. When you smush data structures together, we call that concatenation. Test for membership. So in the same way that in tests to see if a thing is inside of the tuple, it can also test to see if a character is inside of the string. Multiplication is replication, or repetition. So if I wanted to repeat the string a times 100,000, plus arg. There you go. I can produce pain in the computer very easily. And of course, this one's actually, most people forget this by the end of the class where it becomes most useful. But you can also test to see if a string ends with something. So, just, not jumping ahead too far, I hope. When we start learning how to interact with files in the file system, the file names are represented to a program in more or less the same way it would be represented to you inside of your file manager, either Windows file manager or, whatever operating system you have. So, if I have a file, my file.txt, .txt ends with .txt. Oh, let's see, did I mess it up? Yeah, I always capitalize the W when I shouldn't. There you go. Ends with can be used on a file name to test to see whether it's of a particular file extension relatively cheaply and easily. Right? Make sense? Any questions about any of that? Good. So, you've seen me use it many times already. The print function takes a string and outputs it to the console. What you're actually doing is you're taking the characters and loading them into a standard file called standard output, which is periodically polled by the operating system, and anything contained in that file is output to whichever terminal or display is currently active. That's what's actually going on. But, the high school level of description for this is words go in, words come out, in a manner visible. We have also the input function. Now, it's pretty common, if you've ever done Python programming before, you've probably seen the input function because, it's like, input, output comes out, input goes in. This is how you input character information, right? What is actually technically going on with the input function, in the same way that your operating system has standard output, which is periodically polled and outputs characters to the console, you have another file called standard input where keystrokes are logged, and if they are, they can be received from the current process and used, right? But you actually have to, pause the program, wait for the input to occur, normally terminated with pressing enter, and then that can be acquired by the program. So, for example, string or results or answer is equal to input. So the way this works is you provide a prompt, which is a string, inside of the input function, right? So, did you like Elden Ring? Did you like Elden Ring? I don't have a PlayStation. Then the answer that is provided by the user is captured as a string by this process, right? Now, it's very important to realize with the input function, you always get a string from this regardless as to what you think it should be, right? So, for example, if you wanted to say input 2 plus 2 is equal to, right? And you say 4, four is stored as a string rather than as an integer. It doesn't automatically interpret it as being a number, right? You the programmer, can choose to interpret this as an integer, but it requires an additional step. You have to say, answer is converted to an integer, the results of the input function. And then you can see that this is a number again because it's lacking the quotes, right? And if you wanted to interpret it as a floating point number, for example, there you go. Make sense? This conversion step is vitally important if you expect to perform any numeric operations over this data. Performing numeric operations over something that isn't a number will typically result in a syntax or a type error, and atypically, it will actually just do it for you, and you just, will get an unexpected result. Like, for example, if I were to write a quick little function, answer equals input 2 plus 2 equals, and then return answer times 8, right? If I run f, there we go, 2 plus 2 equals 4, without performing the integer conversion, this multiplication at the end doesn't multiply 4 by 8, it repeats the string 8 times, right? So that's because the multiplication operation is, well, we have a fancy term for it in computer science. We call it polymorphic. Have I talked about polymorphism yet? You guys? Anybody? Have I used the term polymorphism? No? Okay. So, reasonably simple concept, but very, very important in computing. When something is polymorphic, poly meaning many and morphos meaning shaped, right? So it's a many-shaped function. It does different things depending on its context, right? Multiplication as applied to an integer is arithmetic multiplication as we would expect to multiply two numbers together, all the way back from elementary school. The same operation, the same operator, is a different operation when applied to different inputs. So this multiplication operator is repetition when applied to data structures. If you do not convert this thing into a number, then it's being used in that sense instead of in the numeric sense, right? So this is like a reasonably easy kind of bug to pick up on, right? Because all you have to do is take a look at the output and be like, well, 4 times 8 is not, 44,444,444. That's nonsense math. So all you really have to do is look at it. But, this can be confusing if you don't know why you got that, right? Make sense? Good. Any questions? Good. Polymorphism, very, very important concept, right? Yeah. If it wasn't for polymorphism, we would have to define a new operation or a new operator for each operation, right? So we would very quickly run out of symbols, basically. And you certainly wouldn't be able to map them onto any keyboard that, you'd need a keyboard like this long. So, yep, good. So, I'll just quickly cover string formatting. So, when you're putting data into a string, there are two ways you can do it. The first is to convert whatever it is you want to insert into the string. You convert that to a string externally to the string and then just concatenate it together. The other is you use string formatting, right? So these little curly brace things inside of the string, you can think of those as slots into which data is being slotted, right? The size and shape of the slot is determined by the character. So if it's an S, then that slot accepts string data. If it's a D, it accepts integer data. You can perform some interesting operations like deciding how many decimal places a floating point number gets printed to, choosing whether it gets displayed in scientific notation or regular notation. You can, these have a lot of options on them. But you'll kind of get, if you go on, you'll see more, because this is like a very standard operation in a lot of languages like C, C++. But for this class, we don't have to worry about it too much. But, you may run into a situation where you want to put things into a string, very probably. But you can do that. I'll demonstrate both ways. So, I am D years old dot format 1 million. Right? It just inserts it. Note, this is not in string format. The string format is implicit on it being formatted into the string. The other way that you can do that is you can say I am plus string convert 1 million years old. You can do it that way. If you do not remember the string conversion, you get a type error because you cannot concatenate an integer, where is it? Yeah. You can't concatenate an integer with a string because an integer isn't a string. It doesn't make any sense. The type errors, by the way, the way that the error reporting system works is it assumes when you have like two incompatible things and you're performing an operation infix like this, it assumes the first one is correct, just for the purposes of reporting the error. So you'll notice this isn't I can't add a string to an integer. This is I can't concatenate an integer to a string because the string came first. And that's assumed correct. Make sense? Good. So yeah, enough said. So here are some very quick programming examples. Frequency. A function to calculate the frequency with which a particular character or substring occurs within a larger string. Very simple. We take the count. We take the count of the number of t's in S. We divide that by the length of S, multiply that by 100, and that gives us the percentage of that string which is composed of that particular character. Make sense? In addition, we can pluralize. So this is an inline if statement, which I kind of detest, but it's in the slides anyway. So the way this works, the way that inline if statements work, it's like A if condition else B. If the condition is true, you go with A. If the condition is false, you go with B. It's the same thing as an if statement that's been split along several lines. It's just all in one line for no particular reason. That's a thing that you find in other languages as well, where it's normally called a ternary operation, but we don't have to worry about that. So if W ends with S, then you append ES on the end. Otherwise, you append S. So duck would be ducks, D-U-C-K-S. Walrus would be W-A-L-R-U-S-E-S after this has been performed. Does that stuff make sense? Good. Yes, and here's the slide explaining the conditional operator after it's been used in a slide. Right? E if true else F is equal to E. E if false else F is equal to F. Right? Don't use it. Use regular if statements. Yeah. So, we just have a couple of more slides and then we'll be finished and on to our next topic. Boolean operators. So we talked about Booleans quite a bit. We talked about how to create a Boolean value using tests, right? Like x is greater than y, 7 is less than 3. These are the types of condition operators that will produce Boolean values. However, it's useful to be able to compose many of those together at once. It's often useful not to merely check to see if x is greater than or less than some other number, but between two numbers, right? This is often a thing. So let's say x is equal to 10, x is greater than 4, x is less than 19, right? How do you test to see if x is greater than 4 and less than 19 at the same time? Well, x is greater than 4 and x is less than 19. Right? Both conditions have to be satisfied in order for this to be the case. So the AND operation, which is also known as Boolean conjunction, both A and C must be true in order for the AND to be true. If either condition is violated, then the whole thing is false. All right? It's this and that. By contrast, OR is this or that. So either one of these things must be true in order for the whole thing to be true. Right? So for example, if we are testing to see if x is outside of a particular range, one way of doing it is reverse these guys. Say OR. Is x less than 4 or greater than 19? Right? In this case, of course, that would be false because it is, inside the range that we're specifying. But if we were to modify it to make it like 39, this condition would then become true. Obviously it's not less than 4 in this scenario, but it is greater than 19, which means the whole thing becomes true because we're using the Boolean OR operator. Make sense? Now, an interesting thing about the OR operation is that OR is true even if both of these guys are true, right? So if B is true and C is true, then B or C is still true, right? Because it is true that either B or C is true, right? Exclusive OR is a special variant of OR operation that excludes the case when both of them are true, right? So let me do a table. This is what I'm about to do on the board is called a truth table. So if we have X and we have Y, true, false, true, false, true, true, false, false. That's all possible combinations represented, right? X and Y is only true if both are true, false otherwise. X or Y is true if either of them are true, false otherwise. X XOR Y is true if either of them are true, but not true if they both are, and not true if they both aren't. Make sense? It's another way you can say this is it's true if they're different and false if they're the same. So it's kind of interesting. Each one of these operations, and there's of course not, which just turns true to false and false to true, which, is so easy that, it has to share a slide. If you dig down into the electronic circuitry that composes your computer, at the very base level, well, one step up from the very base level, which is transistors, every operation that your computer performs is fundamentally encoded in operations of this type, Boolean operations. If you arrange and and OR gates, we call them gates because they're, electronics, right? Okay, brief digression. So electronics, right? If you have an AND gate, right, with two electric signals going in, high and high yields high, otherwise it yields low. This component has this behavior, right? If you take enough of these, mush them all into one big giant circuit, you can do things like addition and subtraction and multiplication and all of the other operations that the CPU implements. All of the operations that the CPU implements are implemented at the basic level in terms of these guys, right? So, yeah, so that's how computers work. Any questions? That's sufficient knowledge for anybody to have about computer to completely reconstruct anything a computer can do, right? So we don't need to have any more classes. Your computer science education is finished now that you know that everything is gates. No relation to Bill Gates, by the way. It's okay, you can laugh at that was a joke. So anyway, so I think we're going to close the topic off there and move on to our next topic. Any lingering comments or concerns about that topic before we move on to statements? We're going to make a statement. No? Okay, cool. So, we're going to talk about statements. Statements are different from expressions, right? Expressions, fundamentally, what we've been talking about so far, these are like sub-pieces of a single line of code, right? The way that you concatenate a string together, or the way that you slice a string, or the way that you index a tuple, or the way that you add two numbers together, it's meaningless unless you store it in memory somehow, right? We already know about assignment. Assignment is a statement, right? The purpose of a program is to take statements of programming code, decode them in terms of their basic operations that are operable on the CPU, and execute those, right? But roughly speaking, statements themselves correspond to lines of code. Generally speaking, what we're going to be talking about mostly in this slide deck is the control structures that we have already briefly introduced. We're going to talk about them in a bit more depth. All right? Good. So, y'all remember the flowcharts, hopefully? Yeah? Okay, I don't have to go over them too awful much. Brief recap. If B then S, we have a condition. If that condition is true, and we all know now that what we mean by condition is we mean Boolean expression. If the Boolean expression evaluates to true, we follow the yes branch. Otherwise, we skip whatever's on the yes branch, right? If then else is the same thing as an if statement, except there's something on the no branch. We do something in the case of no. There's something to do there. Repetition. We have a Boolean condition expression. So long as that conditional expression comes out true, we continuously execute the block of statements represented by S. As soon as this condition is evaluated false, we break from the loop and continue with the rest of the program. So the question then becomes, A, how do we represent this in Python? And B, how do we represent this in Python? So this is the actual Python syntax, which I'm sure all of you will have picked up by now. If B, tab, S. Remember that in Python, a statement being inside of an if statement or a loop is indicated by level of indentation. You always note that you're going to go up a level of indentation because there will be a colon character. Yeah, make sense? Good. So, let's do an example. We're going to explore how loops work. The factorial. How many people have seen factorial before? Most of you. Good. So, for those of you who haven't, the factorial of a number is another number such that it's that number multiplied by the number 1 less than it, multiplied by the number 1 less than it, all the way on down until you hit 1. So it's when you multiply together all of the numbers up to the number that you're taking the factorial of, right? So, the utility of the factorial function is that it allows you to count the number of permutations. So, if, for example, I have a 52 card deck, I think this is how it works, the number of possible shuffled decks is 52 factorial. I believe that's correct, which is an extraordinarily large number. So that's why, you know, a deck of cards is, you know, used in gambling and that sort of thing, because it has a lot of possible outcomes. So, let us, let's implement the factorial function, shall we? Oh, this is winter. Pardonnez-moi. So, define factorial. Takes input n. So, we need to multiply together all of the numbers up to and including n, right? In order to multiply all these numbers together, you're going to have each one of these numbers visible at one time or another, which is to say, some variable in the program must have the value of each of these numbers in sequence. Well, in the factorial's case, it doesn't actually matter if they're in sequence, but you need to have some variable equal to each of these numbers at some point in the program. The easiest way to produce this is using a loop. So, let's say we have some variable I, which starts off at 1, while I is less than or equal to n, we do something, then at the end, we add 1 to I. Actually, you know what? I think I should do this in Python tutor. I think it makes more sense in Python tutor. Good. Now let's call this function. There we go. Print f at 10. Oh, let's do that. All right. So, when the function is called, f not defined. Oh, yeah, that's true, isn't it? There we go. So, once our function starts up, we define I as being 1. We then enter the loop. I is incremented to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, uh-oh. Wow. Good. So notice here, when I is equal to 10, it still does one more execution of the loop. This is going to end up being what we want happening. What we're going to do is we're going to put the statements which perform the multiplication right where this comment is. So by the time we increment it by 1, that part of that section of the code will be over for that iteration, so we won't be putting this invalid value of I into it. So, now we just have to do something. Now, our final value is the product of all of these values of I as the loop is iterated. It makes sense that this should be stored as a variable, since we store lots and lots of numbers as variables. So let's say C for count is equal to 1. or I guess it would be product, so we should use P. P times equals I. That is to say, P is equal to P times I. So now, we have I is 1, we have P is 1. Inside of this loop, you can see that P is gradually being multiplied by every value of I. The value is being accumulated there. And you can see that also that factorial blows up really quickly. So, there we go. And if we wanted to be fancy about it, we would just include a return statement so that, we would actually print something. So then our return value is the value of P, and then that gets printed to our output. The question that this solves, you might be able to write a program that could calculate the value of the factorial of 7. You would even be able to do it the factorial of 23, although the numbers would get very large very quickly. The question is, how do you write a program to calculate any factorial, right? What if the factorial that you're calculating is arbitrary? This is the method that you need. Like, what do I want to say? Another way of doing this, right? A less intelligent way of doing this would be to write something like the following. Def factorial dum n if n is equal to 1, return 1, elif, there we go, n is equal to 2, return 1 times 2, elif n is equal to 3, return 1 times 2 times 3. You see where I'm going with this? If you wrote a long enough program like this, you'd be able to replicate the functionality of this one, right? But that's a lot of writing, And factorials don't, they become so large as to not be very useful at around 25, 30, So in theory, you could do an implementation like this that was done in this manner, and it would work, up to a certain, for all useful values, shall we say. But we can see, I hope, immediately why this is bad practice and this is good practice, right? This algorithm is not adaptable to values outside of specifically indicated received values, right? If you get a value of n that is not dealt with here, then your whole algorithm breaks, right? Whereas with this one, you get literally any value and you can handle it, right? That's because we're using arithmetic and math to calculate it, not expecting certain values. Make sense? Does that make sense? Cool. This is also partially what I mean when I say even a very, very simple program can be written 10,000 different ways. Good. So, in addition, just while we're on the topic of different ways this could be implemented, so in this example, we start at 1 and we count up to n. We could just as easily start at n and count down to 1. Start at n, count down, modify the condition such that I must be greater than 0. And you can see, by the end of it, the value that we get at the end is precisely and exactly the same. It doesn't actually matter because the operation we're performing is multiplication, and multiplication is commutative. Everybody know what commutative means? That's a mathematical property. If you have x, some operator y, being equal to y, the same operator x, that is the property of commutivity. And because this applies to multiplication, it doesn't matter if you do 1 times 2 times 3 times 4, or 4 times 3 times 2 times 1, it's the same result, right? So because multiplication has that property, it doesn't matter what order you perform these operations in. However, if it were something like matrix multiplication, in which ordering does matter, you wouldn't be able to pull a trick like this. But there are many, many different ways you can compose the same algorithm, is the point I'm trying to make. Any questions so far? Good. So far, so good? Right. So, this next series of slides is basically everything I just showed you on Python Tutor, so we'll just skip through it briefly. Yes, their implementation is very slightly different from mine. It uses multiple assignment, which I hate, and it uses, you'll notice that it starts at 0 and multiplies f by I plus 1 and then stops 1 before n. So, like, all of these tiny little mathematical modifications will cancel each other out, essentially, versus the implementation that we just did. So, again, this is another way of writing the same gosh darned algorithm in a slightly different way. When you program, you will make many tiny little design decisions, which will all accumulate and, essentially call your program out as being completely unique to your individual person. Because the tiny little decisions that you make about your program are manifestations of your individual mind, and unless two people have the same mind, they will not write the same program. In the same way that, two people won't, basically all you have to do is write, a couple of hundred characters or a couple of hundred words, and basically you've just through the sheer power of, the permutative ability of character combinations, whatever you write will be completely unique to the person who wrote it. But, so, yes. One interesting point here, which we're going to get into in some depth. Inside of this factorial function, we are defining I and f. In this program, this program asks to print the value of f outside of this function. If you do this, it results in an error. When you declare a variable within a function, that variable is local to that function. What that means is that when the function is declared, or when the function starts up, that variable is created. When the function closes down, that variable is destroyed. We can see this implicitly in the way that Python Tutor displays this, which is actually a lot closer to how the computer actually stores this information than most other ways of visualizing, which is one of the reasons I like Python Tutor so much. So you'll notice we have a list of frames, right? When we start up the factorial function, a new frame is created, and the data that's being used is being used within that frame. The data, like P or I, does not exist inside of the global frame. On and on it goes, calculating, calculating, calculating. Then, once the return value has been decided, that frame is closed. All of the variables contained within destroyed utterly and for all time. There is no way to recover them. Any information which is pertinent must be either returned from the function or stored in what's called a global variable. Local variables are destroyed when the function itself terminates. We have what are called global variables, which are not destroyed when a function that uses them terminates. The reason for this is that they are stored in the global frame, hence the name. So everything in here is preserved no matter how many functions are open, right? So when we return to this, that anything stored there will be preserved. So, for example, let's say we have run count 0, global run count plus equals 1. Then we can run this a few times, print run count. So, you'll notice the run count variable is created within the global stack frame. Within the factorial function itself, this line here, global run count, gives this function permission to access this variable within the global frame. Normally, functions don't have the ability to do this by default. It is via this line here that you give it access. Does that make sense so far? So, you run your algorithm, bing, bang, boom. You'll see that as we're running this, run count is being updated. And finally, when we return to the global stack frame, the 4 instances of factorial that were run, which have now been destroyed, have had no impact on the existence of the run count variable. Make sense? So I've just showed you how to use global variables, but I would be remiss now if I didn't warn you against their use. Global variables, while they seem like they would be very useful, are in fact somewhat dangerous to use. So it has to do with software design principles. It's like not a hard rule, If you have a situation that can only be solved by the use of a global variable, then a global variable is what you should use. However, it works against the principle of modularity, right? So the only thing that keeps software manageable at scale is the idea that if you have a module of software, in this case a function, the inputs and the outputs, like you have the inputs coming in, you have the outputs going out. For the same inputs, you will always get the same output, right? That's the idea. If a software module does not consistently produce the same outputs for the same inputs, then it can't be relied upon to do its job, essentially, and you may not realize that that's the case. It makes software incredibly difficult to debug, because basically, in order to debug something like that, you need much more total knowledge of the system than just the implementation of that single function. So, every time you use a global variable inside of a function, what you're essentially doing is you're designating that variable as an implicit input and an implicit output of that function. Implicit just means that it's like, well, it's like implicit versus explicit. You state it, up front versus you kind of sneak it in, Implicit means that it's not stated directly. So the implicit nature of global variables means that you may not, it's maybe a little bit facetious, or it might be a little bit more obvious, shall we say, in Python, because like there's an explicit global this statement at the top, right? But depending on what language you're using, that may not necessarily be the case. Global variables might just be available for your use. The way that some languages handle them is if you declare a variable of the same name within the function, then inside of that function you mean the local instance that's been defined, but if you do not declare a local instance inside of the function, you just get to use it without worrying about the name or anything. So because it's implicitly both input and output, right? It complicates the inputs and the outputs to the function tremendously. And the more global variables you use, the worse it gets, right? So the way that I've used the global variable in this particular instance is like, that's about the level of it that I'm comfortable with. But you could imagine that if you were, for example, not including an argument here, but using a global variable instead, things would get pretty messy pretty quickly. So, for example, let me just write some terrible code, like really terrible code. Let's say n is equal to 5. Define fact really dumb. Dumb, there we go. Doesn't even take n. Global n. There we go. All that stuff, and return at the end, rather than returning something, we say n is equal to p. So we're taking n, the global variable n, we're taking it as input, doing stuff to it, and then using it as output as well. So let's try running this. So we run through, take 0, position, oh, right. Yes, I need to delete these. Delete. So, should be able to click on this, but anyway. Am I getting an error? S is not defined. What? I didn't put an S in there. That's fake news. It's alright, I don't know. Good. Get out of here. So, yeah, there we go. So in Python Tutor, if you click these, you get like the ability to see where in the program. So we know, we can see that we're already having a problem because, you know, this is how close together the first two of these are. Look how much time it takes to get to the second one, you know? So, oh, what do you mean? Get the power. Got power? Stupid computer. So, essentially, what happens here is n's value in the global frame gets updated at the end of these guys so that, you know, our first value of n is 5. What we thought, we may have thought that we were calculating the factorial of 10 4 times. What we were actually doing is 5 factorial is 120. 120 factorial is the next one it tries to calculate, and you can see that it's just like really large, you know? And then, this really large number, we attempt to calculate the factorial of that, and you can see it just says p is equal to infinity at that point. So, needless to say, not desired behavior. And it's because when you use a global variable, unless you're conscious about resetting that global variable between each call to the function, it's going to just preserve its value from the last time, which may or may not be what you desire, right? So in this case, decidedly undesirable. But if what you're doing is trying to keep track of how many times a function is run, you know, it doesn't really impact the actual execution of the function itself, so it's, you know, fine. Yeah, any questions about that? Global variables are dangerous and should be avoided at all possible junctures. That's your, if you learn nothing else today, learn that. Okay? Good. So, this is kind of the point in the course where I just kind of like, you know, I talk about the slides and I just kind of, you know, yeah. Anyway, okay. So the form that the previous factorial function took was to use one variable for counting and one variable to keep track of what will eventually become the final result. This is a common form for these types of problems. We call it having a counter variable and an accumulator variable. Sometimes you have an accumulator with no counter, sometimes you have a counter with no accumulator. But these are very useful things that you can use to solve a lot of different types of problems. And I know I said specifically that I wasn't going to try to teach you stylistic things so that you could figure things out yourself. But this is like the bare bones basics. So, not every situation calls for them, but these types of numerical examples can be solved relatively easily using this form. In particular, counter variables are very, very, very common. You should think of it as a tool in your toolbox. Make sense? So, Obviously, you can count up, down, sideways, left, right, by 7s, by 3s. However you want to count, all you have to do is set the loop up so that it counts that way. An important thing about accumulator variables is that the accumulator should be set to a value which is correct if the loop doesn't even execute. So, for example, in our factorial example here, what happens if we receive a number which is negative? First of all, what should we expect for a negative number? Possibly some kind of error state. The domain of the factorial function, mathematically speaking, does not include negative numbers, right? So it's possible that you would want to have the thing output some kind of error in this case. What does it do right now, though? If n is negative, right, will I ever be greater than 0? No. So this whole set of statements is never executed. So the return value would be 1. Thank you. The return value would be 1, which, while perhaps not technically mathematically correct, is certainly not like an infinite loop, right? Which is a thing that can happen, right? So, for example, if we were to have this loop set up the other direction, counting up rather than counting down, right? If you were to give it a negative number, it would, like, say you gave this -4, and you were counting up. You could have the program such that it would say -4 times -3 times -2 times -1 times 0 times 1 times 2 times 3 times 4. So you would get 0 as a result, and it would go through all of them, right? That's not necessarily what you want either, right? So these are the types of things that you should think about. The accumulator variable should be correct, assuming the loop never even executes, right? You shouldn't assume, just because you wrote it, that the computer will execute it. Well, no, that's something you should assume. You should never assume that you've written a loop for all possible input cases. Good. So here's a question. Here is a sum function. The purpose of this function is to take the sum of the elements of a tuple. What does it output? I'll give you guys a minute to just read it. Well, 30 seconds anyway. How many people think that this will output 15? A. B, 30. C, error. D, it won't output anything. Okay, we've had like, wow. Okay, and E, people who didn't answer any of those questions. There we go. One honest person. 2, 3, okay. I hope everybody's like just, you gotta interact with the lecture, guys, come on. So, obviously not 15, right? If this were working correctly, it would output 30, right? Because, 5 plus 10 plus 15 is 30. What's the problem with this loop? Yeah?
Doesn't have a counter.
It doesn't, well, the counter here isn't being incremented.
Accumulator.
Yeah, well, S is the accumulator, I is the counter, right? S is being dealt with correctly, but I is never modified within the body of the loop. So, how this would work, I is 0, S is 0, while I is less than the length of t, S plus equals t at I, while I is less than the length of t, it's still 0, right? I is never modified within the body of the loop, so its value never moves from 0. So what you're doing is you're saying s plus 5, s plus 5, s plus 5, s plus 5, s plus 5 ad infinitum. What you have done is you have created an infinite loop by forgetting to update the counter variable. Unless the tuple were to mysteriously vanish and have a length of 0 all of a sudden, this thing would just iterate forever, right? Well, what would actually happen is this thing, like, it depends on how ideal you consider your machine to be, right? Either C error or D doesn't do anything are acceptable in this case. If you add 5, like forever, you'll eventually run out of memory. That will eventually cause an error, but it's sort of up in the air how long it would take to do that, right? The maximum representable integer by Python is exceedingly large. As we saw when we did the factorial example, it was like, time something times 10 to the 193rd power, which is, if you count, because this is essentially counting, even if you, blow out the fact that you're counting by 5s, even if you count, 10 million times a second, it would still probably take something longer than the age of the universe to reach that number. So whether you consider that to be that eventual error that you produce, whether you consider that to be an error, if you want to argue semantics, that would be an error at that point. But over the course of, over probably the rest of the course of the human race, this thing won't output anything, right? So, certainly relative to us in our class, our infinitesimal speck upon the timeline of this planet, this thing wouldn't output anything. Yeah? Question?
So what additional code would you add to make it work?
Very simple. So the question is, what would you add to this to make it work? Very simple. Right here, I plus equals 1. You can fix this with 4 characters. Any other questions? Good. So infinite loops are a big problem. For any program that you're writing in this class, unless it says in the question something like this program could run for a long time if you haven't optimized it correctly, unless there's some statement explicitly to that effect, if you notice the amount of time it takes the algorithm to run, you probably have an infinite loop, right? So when you're in, when you're in the Jupyter environment and you have a cell which is running forever, it's very simple to stop it. You just click the stop button, right? Incidentally, quick little shortcut for all of you. If you want to run the cell that your cursor is currently in, you just hit Shift Enter, and you don't have to go to the taskbar or the toolbar. Very quick. If you notice an asterisk here, that indicates this cell is currently running. So if you see, and otherwise it'll be a little number, which is the number of cells that have been executed so far, including this one that just executed in the notebook. So if you get an asterisk here, this thing is running forever, and you should stop it. In particular, if you're on the server, please stop your infinite loops as quickly as possible, because those things actually do consume like system resources that are being shared by the other students on the server. So, you know, if you could shut those guys down when you encounter them, that would be much appreciated. Like, it's not the end of the world to get an infinite loop, especially if it's like contained in a sandbox like this. It is possible to require your computer system to have a hard reset with an infinite loop, depending on where it occurs. You know, how many Windows users here? Oh, come on, there's more than that. Yeah? Are the rest of you Mac users? Okay, so Windows users, you ever get that thing where like the window grays out and you wait a few seconds and it says this program is not responding? That's normally an infinite loop. So waiting for it to respond, you know how that like only very rarely actually has, you know, that only very rarely works? That's because most of the time that thing is just going to run forever. Because infinite loops. Yeah. If you're in a terminal environment and you want to kill a process, you use Control-C. But yeah. Make sense? Good. Yeah, good. Good. Incidentally, we've already talked about this quite a bit, actually. If you have something and you want to convert it to a different type, you simply use the name of that type as a function. This works even on data structures like tuples and lists and sets and dictionaries and strings. If you want to interpret a string as a number, then you just, you know, put it in there. If the thing you're trying to convert to another format cannot be converted, this will raise an error. That error can be useful. Once we learn how to handle errors, this can actually be used usefully by you, the programmer, but until we hit topic 6, it's just going to be something that you have to deal with. Any questions? Good. So let's talk about if statements. Again. So we've talked about if. We've talked about if-else. There's one more. The elif. Now, elif is a contraction of else if. It's not like a new type of elf in your favorite fantasy role-playing game. So what an else if does is it just inserts another if then else on the else branch of an existing if then else, right? You can compose these infinitely. You can just keep adding new clauses onto the end of this if then else. That's like, you know, if A, else if, elif B, elif C, elif D, elif E, etc., etc. You can have as many of these as you want. The trick with this, we always start at the top and evaluate these conditions in the order that they appear in. The first condition that comes out true, you execute those statements, and then you skip everything that remains in the else if block. Right? Make sense? Good. So let's see an example. Here is a function that determines if a number is even or odd. Remember our good new friend Modulus Operator? You can tell if a number is even by whether or not it evenly divides by 2. If it evenly divides by 2, then the modulus by 2 will be 0. Otherwise, it will be odd because the modulus by 2 will be 1, at least for integer arithmetic. So, if mod 2 is equal to 0, return even, else return odd. So far, so good. This shouldn't be This shouldn't be too far beyond the realms of currently operational mathematics. So let's consider the following slightly more complicated function. We want to write a function that determines whether a number is divisible by 2, 5, or 10. If mod 2 is equal to 0, we return by 2. If mod 5 is equal to 0, by 5. And if mod 10 is 0, then by 10. Right? So what happens if we enter divisibility 5 and divisibility 10? This just indicates that the line is split across two lines. What is the expected output? What do we get from putting 5 into that function? What's our result? Anybody?
By 5.
By 5. What's the result of putting 10 in there?
By 2.
By 2, yes. So this may or may not be what we expected. So divisibility by 10 is, in some ways, a more interesting thing to report than divisibility by 2. A lot fewer numbers are divisible by 10 than by 2. So there's sort of this like implicit principle that you want to report the most interesting and specific information you can, right? So if that's what you intend by this algorithm, otherwise why would you even include this clause, right? This is not precisely what we want. We don't want the 10 case to be caught by 2, right? But 10 is divisible by 2. So the question is, how do we rearrange this program to make that more, like, to have it operate the way that we want it to? Anybody have any ideas? Yes.
Just change the 2 and 10.
Yes. That's one way you can do it, for sure. If you take this condition, swap its position with by 2, the first thing that will be tested is divisibility by 10. So when we put a 10 into it, we hit the first case, we return by 10, right? By 2 is not tested unless 10 didn't come out, right? It's very, very, like this gets at a very important fundamental principle of computing. In these types of languages, which is most programming languages, the computer can only do one thing at a time, right? It can only test this condition, then see if it needs to check the next one, then see if it needs to check the next one. It does not and cannot check all of them simultaneously and pick the one that's like most true. In order for the computer to, like you guys remember from the first lecture that we had, the idea that a computer programmed output cannot be ambiguous, right? If you have multiple cases that would have true conditions if evaluated, it will pick the first one because it can't execute multiple cases, right? That would lead to ambiguous, like the language itself would become ambiguous at that point, right? Do you have a question?
No.
No, okay. All right. No, that's okay. Does that make sense? Question?
So then what's the point of having Elif in it if it only computes at one at a time?
So, that's a good question, right? In this particular instance, it actually doesn't even make any difference. These return statements will exit the function immediately upon being called anyway, right? So, the way that this algorithm is written, if the first condition is true and this statement executes, the function itself closes at that statement, and none of the other cases are even considered for execution, right? But normally, what would happen with an elif statement like this, because this condition came out true, the rest of these would just be skipped, right? Yeah. Does that make sense? Yeah. Question?
How can we change the code to show that it's divisible by 2, 5, and 10?
Okay. you'd have to make some modification. So the question is, if we wanted to, how could we re-implement this function so that we would know if it was divisible by any of these, right? You would do it like this.
Yeah.
There it is. And if we would have to store the string somewhere, which we're outputting. Oh, by the way, 2 quotes directly adjacent to each other means empty string, right? So it's just a string that doesn't contain anything, because we're going to add stuff to it.
So if n
mod2 is equal to 0, s plus equals by 2. So there you go. So I'll show you guys what I did quickly. So if you wanted to indicate multiple of these conditions, you decouple the if statements from each other by removing the else cases, right? So each one of these if statements is now going to be evaluated regardless of the outcome of the previous ones. So if I call this function with, for example, 15, this is false, this is true, so we concatenate by 5 to s, and all of the rest of it is false as well, right? This one, this is like a catch-all case so that it indicates whether or not it's divisible by any of the things that are, dealt with by testing to see if s is still blank, right? Because if s is still blank, then none of these other conditions would have executed. So yeah. So we get by 2, by nothing, by 5, by 2, by 5, by 10. Make sense? I don't particularly like the example, to be honest with you. Like the fact that each one of those cases returns has a return statement contained within it completely invalidates the fact they're even using else ifs in that case, right? Like on the slides here, technically speaking, because the program executes immediately when it reaches any return statement, you could replace these elifs with just plain if statements, and it would not behave differently at all. It would have the same behavior. So I don't particularly like this example, but it is what it is, I suppose. Any questions? Any other questions? That was a good question, thank you. Good. So, yes. So, as you note, we can get more specific information by testing for 10 first. Another way that we can do this, we can test for 2. 2, like the instances where something is divisible by 10 is a subset of instances where it's divisible by 2. So we could test to see if it's divisible by 10 within the if statement where it has already passed as being divisible by 2. If it is, then we return by 10, otherwise we return by 2. Again, both ways, like all of these ways of writing this program have the same functionality. This, again, gets into this idea that I've mentioned several times where you can write the same program 50 million different ways and it all will have the same effect in the end. Now, there are more and less efficient ways to write programs, obviously, but this type of simple if manipulation is like not normally, that doesn't normally have a significant enough impact on runtime to be like worth worrying too much about with respect to optimization. What you really want to focus on with optimization is like reducing the nestedness of nested loops. That you save a lot of time on, but like this type of thing is not normally that, like it doesn't impact runtime that much. It does a little bit, but not much. Good. Another way that you can do this, since things that are divisible by 10 are divisible by both 2 and 5, you can test for divisibility by 2 and 5 and, operate on that basis. Make sense? Good. I'm going to skip the section on Spectre because it's just, I do a lot of examples on the board, so. Very briefly, there was a bug that was relatively famous a few years ago called the Spectre Bug. One of the things that we've been trying to figure out with computers, like shall we say an active area of research in recent years, is hardware manufacturers kind of just dumped these multi-core CPUs on us without really asking us whether we could even, we even had methodologies for handling such things efficiently. So, over time, software people have come to a better and better understanding of how to use multiple cores. But, when multi-core CPUs first came out, it was like, what do we even do with this? You know? All of the programs we've written so far have been for, assuming one line of execution, right? So it took us, we're getting better at it, but it took us some time to get to the idea. So one of the things that they decided that you could use multiple execution cores for was quote unquote if statement branch prediction. So the idea is you have one CPU core that's working on main execution. It sees that there's an if statement upcoming, right? It has another core work on, you have basically one core work on main execution, one figure out what the results of the if statement coming out true will be, another work out what the result of the if statement coming up being false would be, right? And then rather than need to calculate which of the two of these you would, rather than needing to calculate those values, you can just look up whichever branch was correct with respect to the branch predictions made by other CPUs. You could get a speed up this way, right? The problem is that you can trick the CPU into giving you data that it didn't have access to. Essentially, what you could do is you could actually have an attacker program load data from the branch prediction, from the branch predicting CPUs, if you got the timing very, very right. And it's like, this was a reasonably big problem because I think a certain amount of this was baked into the hardware, I think. Might not have been, but you can't fix bugs in hardware because it's physically there, That's why hardware manufacturers go to like a lot of time and expense to try to make sure that everything they do is free of bugs. But yeah, so essentially it was possible to trick the machine into giving information that it shouldn't have access to. And this kind of, you know, this is generally a problem. A very important principle in software design is the principle of least privilege. So this applies to both programs and users, right? You guys are all users. That's what we call people who use computers. So it is a design principle that a person or a program should have no more access to memory or operating system resources than is necessary for the operation of what it is they're trying to do, right? This is why your computer doesn't give you administrative privileges all the time, right? If you're installing a program, you know, in Windows you get this little pop-up that says, oh, are you sure this program is trying to install itself? Are you okay with that? It's like, what it's actually doing is it's like, are you choosing to invoke administrator privilege for the purposes of installing this program? And you always click yes, but it doesn't tell you that's what it's doing because it's Windows, because Windows feels it has to talk to you like you're a 7-year-old. Like, I've been noticing with like even like their shutdown messages, like they're talking to you increasingly like you're a child, you know. But anyway, screw Windows and everything they stand for. But anyway, so the idea is, if your user profile were ever co-opted by a malicious program, it would not be able to install software, in theory, at least software that was like properly installed. It would not be able to do that because you would need like an official click-through from a user to be able to do that, right? In Linux, the way that it works is they call it super user, and you have to enter super user mode in order to perform certain operations, like overwrite your, you know, like write to files that are part of the operating system, and, you know, mess with other users' data and stuff like that. You need super user privileges. The whole point of that is, if you give people or programs access to more than they need, they can mess things up that they shouldn't be allowed to through either malice or stupidity. So, in the case of programs, you know, well, programs can be both malicious and stupid, but yeah. So you want to restrict the permissions, right? Basically, anytime you have a situation where some user or program is permitted more access than they deserve, a hacker is going to find that and exploit it for, you know, whatever gain hackers get out of such things. So a very large component of computer security is making sure that the permission system is never violated. And also designing your system in such a way that people can't access stuff they don't need to see. But yeah, anyway. So class is supposed to end at 12:20. It's now 12:01, which means that we're done class. Awesome. Thank you very much for your time and attention, folks. See you tomorrow.